Great. Okay. All right. So hello again. So today I'm going to talk more about intrinsic triangulations. And let's see if we do this. There we go. So this time I'm going to talk a little bit more about the algorithm side. So just as a reminder, the high-level idea was that rather than working with an ordinary triangle mesh in R3, we're going to allow ourselves to draw other triangulations on top of the same polyhedral surface, where the edges can now be straight paths along the surface rather than just straight segments in Euclidean space. Okay, or kind of like our more abstract picture was to say we have connectivity plus edge lengths rather than vertex positions. Okay, so yesterday we talked a little bit about just basic background and also a couple data structures for representing these triangulations. Today I want to talk a little bit more about algorithms, so in particular building a discrete Laplace operator, which has all sorts of applications, and also computing geodesic paths. And I'll end with some interesting open questions about this whole area. Okay, so first up is the Laplacian, which I've mentioned a number of times yesterday, that this is something that gets used all over geometry processing. And so this is some work with Nick Sharp on defining a new Laplace operator that really works on all triangle meshes, not just special kinds of triangle meshes. And in particular, so far we've been making this simplifying assumption that all of our geometry is manifold, okay, meaning it's a triangulation of some manifold surface. And in the simplicial case, you can characterize these triangulations by saying that the link of every interior vertex is just a single loop of edges, and the link of every boundary vertex is a path of edges. Another way of looking at this is to say, okay, if I look at an edge in a manifold triangulation, it has just two triangles containing it, or if it's on the boundary, it has just one triangle containing it. So if I have more than two triangles incident on an edge, I'll call that a non-manifold edge. Likewise, a vertex in a manifold triangulation is going to be just a single kind of cone of triangles, whereas in a non-manifold vertex, you might have multiple cones touching that vertex. Okay, and so we often make this simplifying assumption to make algorithms easier to write down and easier to reason about, but the reality is data in the real world is not always manifold, and we really would like to build algorithms that work on all meshes, not just manifold meshes. And so what we're going to do is introduce this idea of a tufted cover, that's what we call it, to extend this whole machinery of intrinsic triangulations to non-manifold triangle meshes. And what that's going to let us do is kind of run standard manifold algorithms on non-manifold data, at least in a lot of important cases. And also, interestingly enough, this is going to let us extend this same machinery to point clouds. So by triangulating point in a certain way, we're going to again be able to bridge between nice sort of standard manifold mesh processing and point cloud processing. Okay, so one question is, why do we have non-manifold data in the first place? Well, one reason is that a lot of 3D models are built purely for visualization purposes. The people who are creating these don't care about whether they can do processing or PDEs or whatever, but somewhere down the line, it might actually be useful to be able to do this kind of processing. Another is that algorithms may just produce things that have defects, that have non-manifold outputs. So maybe I'm reconstructing a surface, even though that surface really is manifold, I have these topological defects in my reconstruction. But these aren't always errors. So sometimes I have like physical problems where they're actually non-manifold features, maybe in foams or where multiple interacting liquids meet or whatever. Also today, we're going to look at a case where it's useful to just be able to do kind of a sloppy triangulation of a point cloud, which becomes super non-manifold, but still work with this kind of data. Okay, and so maybe the high level here is that non-manifold meshes, you know, as much as kind of in an academic setting, you might think of this as a kind of a nasty case. Well, this is what most people in the real world who want to work with geometric data just call it a mesh, right? They don't call it a non-manifold mesh or a manifold mesh. They just say, hey, I have this mesh. I need to do something with it. And so that's why we want to build algorithms that handle this general case. Okay, so the central example we're going to look at is how do we define the Laplacian for I think somebody's got their microphone on. Okay, so the central example we're going to look at is how do we define a Laplace operator for general triangle meshes? And if you go and open up your textbook definition of Laplace-Beltrami operator, okay, usually this is defined on something that has a manifold structure. But if you think about like what is the idea that's captured by the Laplace operator, well, there's actually a lot of characterizations of the Laplacian that are perfectly meaningful for non-manifold domains. So one is to imagine that my non-manifold domain, you can imagine I take like steel sheets and I literally weld them together in some non-manifold way. Well, this thing still can carry heat. I can still talk about heat diffusion through these metal sheets. And so I could say, kind of turn the heat equation around and say that the definition of my Laplacian is going to be the time derivative of heat as it diffuses through this domain. Another way of looking at this is to say, okay, if I have some non-manifold domain, let's say 2-dimensional, I could thicken it by balls of radius epsilon, and I would get a manifold 3-dimensional domain. This thing has a perfectly well-defined Laplace operator. And then I could kind of take the limit as I shrink epsilon back down to 0. Okay, and so the non-manifold surface mesh Laplacian that we build today is actually going to give results that are very similar to what you would get by just building a volumetric Laplacian on a thickened version of the surface. And there's other ways you could think about this. So Laplacian measures the deviation from a local average. You can think about it in terms of variation of surface area and so forth. There are a lot of ways to think about, what does it mean to talk about Laplacian on a non-manifold domain? Okay, so recall that our basic approach to improving triangulations in this intrinsic setting was to perform intrinsic edge flips. And when we have this non-manifold data, we run into a very basic problem, which is, well, what do you mean by flip a non-manifold edge? Right? Before it was you replace two triangles with two other triangles that describe the same intrinsic geometry. Now it's not clear. You think about this extrinsically or intrinsically, like what exactly would it mean to flip an edge? And actually, we're not going to answer this question. We're going to sidestep this question. And we're going to say, well, here's a useful observation. Many of the objects that we want to construct and work with in geometry processing will require the edges to be manifold, but it doesn't matter if the vertices are non-manifold. This isn't going to cause us any pain. So our strange idea for making this all work is to say, how about we do a transformation of our mesh that makes all the edges manifold at the cost of making every vertex non-manifold. Okay, kind of a weird idea. So how do we do this? Well, in short, we're going to make 2 copies of every triangle and then identify all the duplicated vertices. So glue all the vertices back together. And I'll give a more precise construction in a minute. But once we do this, everything's edge manifold, and we can just flip edges as usual, right? So something like this, we build this tufted double cover, and then we're able to flip edges just like we're on a manifold surface. Right? Edge flip doesn't require manifold vertices, it only requires manifold edges. And so at a global level, this is what these tufted covers look like. I start with the red surface, and I'm going to build this kind of funny covering of it, this blue surface, which if you kind of puff out the triangles, reminds you of tufted upholstery. So you can imagine each vertex of the original mesh is kind of a button on this tufted sofa. Okay, just to be clear, by the way, I'm not actually going to change the geometry. I'm just displacing the surface in this way for visualization purposes only. Okay, so when you see these blue pictures, the geometry is still exactly this red geometry that we started with, just kind of 2 copies of it. Okay, so how specifically do we build this tufted cover? Well, step 1 is we just go to each triangle, we make 2 copies of each face, but then we glue the vertices back together. Okay, and then we take these doubled faces and we glue adjacent copies around each edge. So front to back, front to back, front to back. Okay. And to do this, we need some ordering of the faces around an edge. If we have a mesh that's embedded in space, what we're going to do is just take the ordering given by the embedding. Okay. And we'll see later that it doesn't really matter so much the order of this gluing. Okay. So that's nice. So now we have all edges that are manifold. Vertices are not manifold. And we can build a high quality Laplacian for this new object, and in turn for any triangle mesh in a straightforward way. So we take our input triangle mesh, we construct this tufted cover, and then we flip just as before to an intrinsic Delaunay triangulation, right? Now we're able to flip all these edges. We can run this greedy flipping algorithm until all edges are Delaunay. Okay, and on this final domain, we build the usual cotan Laplace matrix. We just build the usual finite element stiffness matrix. Or you can imagine if you have other matrices you want to build, other operators you want to build, okay, just use this domain that is now kind of nice and edge manifold. Okay, once we've built this Laplace matrix, we're just gonna, the way that we build this Laplace matrix is we just sum up for each triangle the local 3x3 stiffness matrix. Right, so there's no ambiguity about how to define this thing. So here's really the key point. Since the vertex set is unchanged, right, we glued all of the double vertices back together, the matrix that we get out of this process is still just a V by V matrix where V is the number of vertices in the input mesh. So this is a Laplace operator actually not for this strange double cover, but actually for the original non-manifold triangle mesh. Okay, but the good news is because of the way we constructed this, the edge weights are now guaranteed to be positive. right? This has all the same nice properties as the intrinsic Delaunay Laplace matrix. And so in practice, what this means is we're going to get a lot more accurate and reliable results when we use this Laplacian for geometry processing. Also, just to be clear, if we don't do these Delaunay flips, then actually the matrix we get out, the operator we get out, is just going to be the standard cotan Laplace, right? So it really is the combination of building this tufted cover and doing these intrinsic Delaunay flips that makes this all possible. So here's kind of a diagram of how this works. We take our input, we build the cover, we flip to Delaunay, we output this high quality matrix. And again, this is a case where all of these weird ideas can be encapsulated in some black box that the user never has to think about, right? They just click a button, all this stuff happens under the hood, spits back out a V by V matrix that they can use for their geometry processing, just like they would with any other Laplace matrix. Okay. I'll just pause here for one little open question, which is about locality. Okay, so when people talk about discrete Laplace operators, they kind of say, well, what properties does this discrete operator have? And do those properties resemble the continuous Laplace-Beltrami operator? Right, so we'd really like something that at least, forget about convergence for a moment, it should at least preserve some structural properties of the Laplacian. One basic property is symmetry or self-adjointness. Okay, well, we get that because we're just using, again, the standard cotan Laplace matrix on this new domain. One is that linear function should be in the kernel. So if we have a planar domain and we have a linear function u, this should be a discrete harmonic function. We get that again because we're using this cotan weights. One is that all the edge weights should be positive, right, which implies a maximum principle for discrete harmonic functions. So this is something that happens in the smooth setting, should also happen in the discrete setting. And we get that here because of the intrinsic Delaunay property. Because we flipped to intrinsic Delaunay, all of our edge weights will be positive. Okay, one last property that people kind of look for in these discrete Laplace operators is locality. So in the smooth setting, a differential operator is local, right? The result depends only on the values of the function in an arbitrarily small geometric neighborhood around each point. Okay, that's what it kind of means to be a differential operator. And so the question is, how do you translate this locality condition to the discrete setting? Well, one proposal is to say that the value of this discrete function at a vertex I depends only on values at vertices j no more than k edges away in the input triangulation. So if I walk from I to j, that should be a distance of no more than k edges for some universally fixed k. Okay, and that has been kind of the definition that's considered in the past. But I would kind of ask, well, this is a little bit weird from the perspective of building this intrinsic Laplace operator, because what is so special about the edges in the input triangulation? This is something that we've kind of said a couple times. In fact, that Tullio Regge said, these edges that you use to describe the metric are really not special in any way. So why are we caring so much about this combinatorial edge distance, right? And in fact, this combinatorial distance can actually be very different in general from the geometric distance. So my input mesh could look like this, right? And there's vertices that are one edge away. They're actually quite far away geometrically. And so, on the flip side, if you look at the Delaunay triangulation, something nice about this intrinsic Delaunay triangulation is that at very least, that for every vertex, the geodesically closest vertex will always be contained in the triangulation. And so in some sense, this intrinsic Delaunay triangulation might be considered kind of more local than the input triangulation. But I'd really like to have kind of a more precise discussion about this, right? What is a good notion of discrete locality that really captures the property that you have in the smooth setting, this geometric locality? Okay, but that's just kind of an aside. One nice property that this Laplacian really does have is that even for manifold domains, it provides better behavior near the boundary than either the cotan Laplacian or even this intrinsic Laplacian that we looked at yesterday. And the reason basically is that if you have an obtuse angle in a boundary triangle, then the boundary edge will still have a negative weight. And because you can't traditionally flip this boundary edge, there's no way to get the Delaunay property on this boundary edge. You can't get positive edge weights, right? Whereas in our tufted cover, we have this doubling of the surface, and so I can actually flip the boundary edge. It'll kind of wrap around the boundary, and we can ensure this Delaunay property everywhere. And so what this means in practice is, let's say I want to do some kind of data interpolation, right? So I have a value 1 at one vertex, I have a value 0 at another vertex, and I want the smoothest function everywhere else, okay, which I can do by minimizing the Dirichlet energy or computing a discrete harmonic function. if I do this using the cotangent Laplace or this intrinsic Laplacian, then I can get values that actually go outside the initial range of the data. So rather than interpolation, I get kind of extrapolation. Whereas if we do this with this tufted Laplacian, we're guaranteed to stay within the bounds. Right? We actually get this interpolation property. So that's nice. Here's just one example of a problem where we really want to compute non-manifold surfaces, which is computing minimal surfaces, or these kind of soap films. So you take a piece of wire, you dip it into soapy water, you pull it out, and there's all these interesting shapes that can emerge, which are area minimizing surfaces or zero mean curvature surfaces. One good algorithm for computing these things on a triangle mesh is given by Pinkel and Poultier. Basically, you build the Laplace matrix for your current mesh, you solve for a discrete harmonic function with respect to this current Laplacian, and then that discrete harmonic function defines your new vertex positions. You repeat this until convergence. If we do this with our non-manifold Laplacian, we can produce these really nice, cool non-manifold soap bubbles, even on really, really awful meshes. So if you look closely at the bottom here, you see that this is like a really awful triangulation of the domain. And if we compare it to what you get with the standard cotangent Laplacian, well, there you can get violations of this maximum principle. So that shows up here as surfaces that are discrete harmonic, or sorry, that are discretely minimal, but have these places where clearly you could make the area smaller, right? They're really not geometrically minimal surfaces. Okay, here's another kind of more practical task in geometry processing, which is differential surface editing. So the task is you want to take a shape and deform it by interpolating some transformations at these kind of control handles. So here's kind of a crazy example where we've taken a mesh that was produced by doing a mesh Boolean of lots of separate, disconnected components. And so you get this crazy non-manifold mesh, but you'd still like to animate it. So you pull these control handles around and you want to compute this deformation. If we just apply the standard cotangent Laplacian, well, we get a mess of garbage. If we use this tufted Laplacian, we get at least a reasonable deformation of the surface. One thing you might ask is, well, what about this ordering of the faces around the edges? So before we said that we order the faces around an edge, when we do this gluing together of the triangles, we order by the order given by the extrinsic embedding. What if you just had intrinsic data, right? How would you do this gluing? Well, we can at least check that if we do other orderings for this gluing, like we order by random choice, or we do it by triangle area or whatever, the result you get is very, very similar. And the basic reason for this is that all of these different orderings essentially define very, very similar function spaces on the original domain. So I think that's the right way to look at this, is what are the kind of finite element bases that you're making available by building this double cover, or this tufted cover. Okay, so finally, so far we've been talking all this time about meshes, but an increasingly popular geometric representation, for instance, in machine learning, are point clouds, so just disconnected points in R3. And there are a few different ways that people have defined point cloud Laplacians over time. And these have some nice properties. For instance, you can get pointwise convergence, which is something you don't get traditionally from kind of like the cotangent Laplacian. But on the other hand, these point cloud Laplacians, to get these properties, generally require some pretty dense sampling. And kind of from a practical perspective, the matrices have a huge number of non-zeros. So with a mesh-based Laplacian, you can argue pretty easily that you have about 6 non-zeros or about 7 non-zeros in each row. Whereas these point cloud Laplacians are going to have a huge number of non-zeros in each row, which means they become much more expensive to factor and store and so forth. Also, if you've ever actually worked with these in practice, rather than just kind of read the papers, you'll find that they have some really hard to tune parameters. If you try to get these working on real geometric algorithms, it's really a pain in the butt to get these working on real data. And so the hope is to be able to kind of create a bridge between these nice sparse Laplace operators that we have for meshes and point cloud processing. And the idea for how to do this is we're going to go to each point. We're going to find its local neighbors and then triangulate them, okay, by projecting them into a local estimate of the tangent plane, constructing a Delaunay triangulation. Then we're going to take that combinatorics, throw away the geometry of these projected points, but just take the combinatorics of those triangulations and just kind of take their union, right? So take the union of all these triangulations. Well, this gives us this really crazy kind of non-manifold mesh, but no problem. We now have a way of dealing with non-manifold meshes. We can build this tufted cover. And on top of that tufted cover, we build this tufted Laplacian with all these nice properties. Okay, so this final Laplacian looks a lot like a standard mesh Laplacian. It's very sparse. It has the same kind of accuracy as cotangent Laplace, linear precision, symmetry, all these nice properties. and it's guaranteed to have positive edge weights, so you get a maximum principal. If you compare how these things behave in practice, it really does pay off. So here, for instance, we're going to compute a harmonic Green's function on this point cloud. And if you look at kind of previous Laplacians, you might get underflow, you might get negative values, all sorts of things kind of go bad numerically. Whereas with the Tufted Laplacian, because we have these clear guarantees, everything works out as you might expect. Okay. At a broader level, what's really nice about this construction is that it allows us to kind of provide a bridge between existing algorithms for meshes and processing on point clouds. So for instance, let's say you want to compute a conformal parameterization of a point cloud. Well, good news, we already have lots of algorithms to do that with meshes. And now we can just kind of plug those in through our Laplacian and do it also for point clouds. Or we can compute here the logarithmic map, or there's all sorts of other things you can imagine doing. Okay, so that's it for Laplacian. Let's now talk about a different task, which is computing geodesic paths. And this is, again, work with Nick Sharp. So the problem statement here is I'm given some curve on a surface. And what I'd like to do is find a locally shortest path, or a geodesic, in the same isotopy class. Okay, so for instance, if I start with this red path, I would like to turn it into this nice, smooth, straight path. Or if I start with this more interesting example, this path, I'm happy to turn it into this path, okay, which is a geodesic. It's a locally shortest path, even though it's not a globally shortest path. Right? I could definitely find a shorter geodesic by just connecting the two marked points directly. Okay. So this is kind of important. This word geodesic is very often confused especially by a lot of kind of people in practical geometry processing with the idea of a globally shortest path. Okay, but the reality is that actually many algorithms in geometry processing really need to find these curves that are not just the shortest path. So other interesting geodesics beyond the shortest path. So whether you're computing cut graphs or segmentation boundaries or Bézier curves or whatever it is. Another thing you can think about is, why are we thinking about this isotopy condition? Why do we want isotopic paths for geometry processing? Well, one is that isotopy is a really natural requirement when curves describe regions, boundaries of regions. Right? So just as a simple example, let's say that I have these two regions on my surface and I have curves that delineate their boundaries, and I want to straighten out those curves. Well, if I just straighten out those curves and don't think about these isotopy classes, I'm going to end up with something like this. I have these curves that intersect and I don't know anymore, what is the partition of the surface into these regions. Whereas if I do this kind of isotopic straightening, I preserve this kind of partition or segmentation. Okay, so how can we actually compute these curves? How can we shorten curves on polyhedral surfaces? Well, one very natural idea would be to say, let's just think about it in kind of a Lagrangian way. I'm going to encode the curve as a sequence of edge crossings, and I'm going to iteratively shorten my path one vertex at a time. So I might start with a path like this, and then straighten one vertex, and then another vertex, and so forth. There are a few challenges with this approach. One is that, well, at least for the kind of most naive algorithm, it's kind of hard to guarantee convergence. You have to think pretty hard about how things behave around vertices. Probably can be done. But there's other challenges. For instance, if you're storing paths for the single source geodesic problem, I want a path from some source to all other vertices, then this is going to take something like order n squared storage, so not particularly efficient. And also, even if you just think about this style of algorithm in the plane, it's going to converge very slowly, only in the limit of refinement, right? So you're going to shorten and shorten and shorten and shorten and shorten, but this is like Zeno's paradox. You never actually reach the geodesic. You only get arbitrary close, and you make less progress on each iteration. Okay? So we're going to take a different approach, and the basic observation is, thinking from this intrinsic perspective, that the edges of an intrinsic triangulation are already geodesic segments. So rather than sliding the vertices of a curve around on some fixed triangulation, what we're going to do is modify the triangulation itself so that the curve that we're looking for is a sequence of edges in this new triangulation. Right? We're going to take advantage of the fact that we have all these different intrinsic triangulations of the surface. And that perspective leads to a remarkably simple algorithm, which in short just says greedily flip edges until the triangulation contains the desired geodesic paths. Greedily flip the edges until the path can't be made any shorter, essentially. So this is very similar in spirit to Lawson's algorithm, right? For finding a Delaunay triangulation, just greedily flip edges until you get the object you want. And there are actually other algorithms in this world of intrinsic geometry, intrinsic triangulations that have this greedy flavor. So some nice features of this particular algorithm is, well, unlike this more Lagrangian representation, the configuration space for the problem is now discrete, right? We're making moves between nodes in the flip graph every time we do one of these edge flips. And so what that means is we can reach the exact solution in finitely many steps or finitely many edges in this flip graph. In practice, this algorithm is extremely fast, so it only takes like milliseconds for meshes with millions of triangles. Like the kind of smooth curve shortening flow, you see properties that you might expect. So embedded loops remain embedded and they shrink to geodesics or points in finite time. And most importantly for us, we can use this for a lot of general problems in geometry processing. So not just geodesic paths, but also geodesic loops and curve networks and other things that show up in applications. Here's a little just kind of sneak preview of what happens if we run this algorithm. So if I, oops, sorry about that. Okay. Let's try this again. There we go. So here's just a little sneak preview of what happens with this algorithm. So I start flipping and flipping and flipping, and what you see is this curve gets shorter and shorter and shorter. Again, something like a curvature flow, but not exactly, right? We're not making progress at the same rate at every part of this curve, but it is getting shorter and shorter and shorter until finally it reaches a geodesic. I'll point out here, by the way, that even though it looks like we're doing lots of edge flips, and we're doing 11,000 edge flips, in terms of real time, this is actually only taking about 1/100th of a second to get to the final solution. Here's another example that we can see a little bit more up close. So this is tightening a loop into a geodesic. And what you notice here is that we kind of leave this wake of triangles, of kind of bad looking triangles behind the curve as we flip. And this actually isn't a really big problem because, as we discussed yesterday, we have some really robust data structures for representing these triangulations. But if you do want a good triangulation after this is all over with, well, the good news is we're already in the setting where we know how to come up with good triangulations, right? We're in this kind of edge flipping setting. We say, okay, first let's flip all our edges to get our geodesic. Once we're done with that, we can flip all our edges to make the mesh nicer, to get a Delaunay triangulation, or maybe we do some refinement to get even higher quality. And this is kind of one of the real points of doing things this way, is not just to compute geodesics, but to realize that this kind of gives a nice way of unifying curve processing and surface triangulation on these polyhedral surfaces. And this starts to look a little bit, in some sense, like more old-fashioned computational geometry, where we can talk about straight segments and straight segments in triangulations. And I'll touch on that a bit more later on. Okay, so how does this actually work? So before we give the algorithm, we have to at least agree on a definition of what does it mean to be a discrete geodesic. So in the smooth setting, geodesics actually have two equivalent characterization. We can say that they're curves that are both straightest and locally shortest. There's no acceleration. And if I look at any little piece, I couldn't possibly make it any shorter. Okay. In the discrete setting, interestingly enough, at least in polyhedral surfaces, these two notions of geodesic no longer agree. Right? Shortest and straightest can be different. So for instance, if I have a curve near a positively curved vertex, then I can have a straight path that goes exactly through a vertex. But it actually turns out that a locally shortest path can never go through a positively curved vertex. I can always make it a little bit shorter by going around the cone tip rather than going straight through the cone tip. Okay, so we have to pick one or the other. Which one do we consider to be geodesic? In our case, we're going to seek locally shortest geodesics, and this corresponds to the same notion of exact polyhedral geodesics that are used in classic algorithms from computational geometry like Mitchell-Papadimitriou. I also just want to make it really clear, we are looking for exact polyhedral geodesics, so curves that are really geodesic with respect to the polyhedral metric. We're not looking for just numerical approximations like using PDEs or something like that. Okay, so what does a locally shortest curve look like on a polyhedral surface? We can get a little more detailed here. Well, if we consider a curve made by a sequence of edges, then at least at each vertex alpha, we're going to let alpha min and alpha max be the smaller and larger angle on either side of the curve. Okay, and we're also going to let capital theta be the sum of these two, just the total angle around the vertex. Okay, so it turns out that a curve is locally shortest at this vertex if and only if the smaller of the two angles is greater than or equal to pi. Right? So for instance, if this was flat, if this is a triangulation of a planar region, then alpha min would just be pi at a straight line going through that vertex. Okay. More generally, what we see from this is that a locally shortest geodesic cannot pass through a positively curved vertex, right? Because the total angle is always less than 2 pi. On the other hand, there are actually many different ways for a locally shortest geodesic to pass through a negatively curved vertex or a saddle vertex. So what that means is if we have a locally shortest geodesic path, it's going to be a sequence of edges that connect negatively curved vertices, or maybe in kind of a degenerate case, perfectly flat vertices, but no cone vertices or no positive cone vertices. Okay. So how do we actually find these paths now that we have a clear definition? Well, the atomic operation in this loss and flip algorithm was just to greedily flip non-Delaunay edges. The sort of atomic operation in our algorithm will be to greedily flip edges at vertices that are not yet locally shortest. So at vertices where we can make some kind of progress. And so intuitively, what this means is we're going to pick some vertex on our curve that's not yet locally straightest, locally shortest. And then we're going to try to pull this vertex tight, or the path at this vertex as tight as possible without it crossing any other vertices. So in this picture, we're going to turn the original path into this dashed line. How we're going to do that is we're going to start flipping edges in this blue wedge next to the vertex, this smaller wedge next to the vertex, until that wedge contains the new path that we want. Okay, and then we can just slide this path over. That's also, by the way, how we know that this is isotopic to the original path. Each of our local motions is an isotopy. Okay. Okay, so more precisely, consider some vertex B where the smaller angle alpha min is less than pi. Okay, like this vertex here. What this algorithm does, and I'm going to call this flip out because we're going to flip edges out of this wedge. Okay, so the input to this algorithm is going to be the consecutive vertices A, B, and C along the path. And what we're going to do is, while we can find any angle beta sub I that's less than pi along this left boundary of the wedge, we're going to flip the first such edge BI that has this angle less than pi in counterclockwise order. Okay, and then we're going to output the shorter path along the remaining boundary. So I think this gets a lot clearer just to see the example. So in this example, the first vertex looks like this. I guess this is going to be in clockwise order, but it doesn't matter. So the first vertex looks like this, beta I. So I'm going to flip this edge. Okay, there's another angle beta I that's less than pi. I'm going to flip that edge. Here's another one that's less than pi. I'm going to flip that edge. Okay, and this is a particularly simple case because now there's just one edge remaining. And if I slide the path over, now I get a shorter curve. Okay, so why should this work in general, right? What we want to prove is that this little procedure always yields a shorter path. And so what we need to do is show three things. First, and this is just going to be a little sketch. I'm not going to go through this proof precisely. So the sketch is that any edge that we need to flip in this process can be flipped. So basically, we want to prove that we actually can run this algorithm. To do that, we need to show that kind of what we discussed yesterday. To flip an edge in an intrinsic triangulation, it has to form a convex pair. Otherwise, this flip might make the mesh kind of fold over itself. And also, both endpoints have to have degree greater than 1, because otherwise I'd do a flip that would leave a cone point in the middle of a triangle. Okay, so that's the first thing we have to show. We can flip the edges that we need to. Second, that we're going to make progress, so that flipping an edge in this wedge always decreases the number of edges that needed to be flipped. And third, we need to show that upon termination, this new boundary on the other side of the wedge is actually shorter than the initial pair of edges in our path. Okay, and so just to keep this short, I'm gonna sketch out this proof, but I'm gonna make a simplifying assumption that we're working with a simplicial complex. So remember that we said in general, an intrinsic triangulation can be a delta complex. We can have edges of triangles glued to themselves and so forth. Writing the proof for the more general case is reasonably straightforward, but it's quite annoying. It takes a few pages of not particularly insightful arguments to make this work. Okay, so step number one is we want to show that edges are actually flippable. So let's say that BI in this diagram is the next edge that we need to flip. Well, one thing we can notice is that the associated edge diamond is always convex. Why? Well, for one thing, we chose this corner because beta I is less than pi. That's the only reason we're trying to flip this edge. Second, both the top and the bottom angles are theta I minus 1 and theta I plus 1. Those are both less than pi because they're corners of triangles, period. Right? Triangles have angle sum less than pi. Okay? And then the remaining corner has to be angle less than pi as well, because that's why we're here. That's why we're at this vertex. We said this vertex is not yet locally shortest, which is equivalent to saying this minimum angle is less than pi. Okay? And so since we know that all four angles of this quad are less than pi, it has to be a convex quad. Okay? The other thing we need to show is that the endpoints are degree greater than 1. And why is that true in the simplicial case? Well, that's quite easy. In a simplicial complex, all edges have endpoints of degree greater than 1. Okay, so this is something where the delta complex case is the only interesting thing to consider. Okay, so hence, at least in the simplicial case, this edge is flippable, and we just need to take some additional care to show this works in the general case. Okay, step 2 is we want to show that we actually make some progress. So flipping this edge bi always decreases the degree of the vertex that we're shortening. Why is this true? Well, because in the simplicial case, these four vertices are always distinct, right? We can't have any strange gluings. So the four vertices, I, B, I plus 1, I minus 1, they're always distinct vertices. And so when we do this edge flip, we're going to kind of kick out this vertex I. It's no longer part of the region that we're considering. In the more general case, we can actually have this weird situation where we have edges which are incident on B, and both endpoints are incident on B at corners that are inside this wedge that we're considering. Okay, so it's a mouthful, really hard case to think about, hard to draw pictures of this thing, but it can happen. But you can still argue that everything works out just fine. Okay, so basically you argue that the degree always decreases on at least one of the two endpoints and cannot increase on the other one. Okay, and then the final step is kind of got a cute argument. So the algorithm is going to stop. We're going to stop flipping edges when all the remaining angles along the left side of this wedge are greater than or equal to pi, right? So we start out with this figure. We look at that. Okay, there's an angle less than pi, so we flip it. Angle less than pi, we flip it. And now we're left with only angles that are greater than pi, which means the path along the left side is convex. It's a convex curve contained in the convex hull of the original 3 points A, B, and C. So why is it that this curve along the left side must be shorter than the curve ABC, the one that we started with? Well, one way to argue this is something called the Crofton formula, which says that the length of any curve is proportional to the expected number of intersections with a random line. And so what you can say is, okay, well, if I were to hit this figure with a random line, then every line that intersects the inner path also intersects the outer path, right? At least as many times. But we could have lines that intersect the outer path that don't intersect the inner one. Hence, the inner path is shorter. Okay? And so we can always shorten the curve by taking the left path rather than the right path. And that's kind of the end of the proof. Okay? So from here, now that we know how to locally shorten a curve, we can shorten it at one vertex. How do we shorten the whole curve? Well, okay, this is pretty straightforward. We just say, while the curve is not locally shortest, apply this procedure to the smallest wedge. Looks like Jack has a question.
Yeah, I'm just wondering, are we still in the situation where you're working with your tufted representation?
Nope, sorry, that was a whole other.
Okay, all right.
That was
yeah, no,
Yep.
Yeah, got it.
Sure, yeah, sorry for not making that clear. Okay. Okay, so how do we shorten the whole curve? We just keep shortening any vertex that is not yet locally shortest. And so if we start with a non-crossing curve with fixed endpoints, we're going to get a non-crossing geodesic in the same isotopic class relative to its endpoints. What do I mean by non-crossing? I just mean that if I make a epsilon perturbation, I can remove any non-injectivity by making an epsilon perturbation. Okay, so here's an important theorem about this, right? You might ask, okay, sure. So we know that the local procedure shortens the curve with a finite number of operations. But what about this global procedure? Couldn't I end up in the situation where I keep shortening local vertices one after another, but never reach a geodesic, a locally shortest geodesic? Well, the theorem is that this procedure in the box always takes a finite number of flips. And kind of the crux of this proof is to use the fact that there are a finite number of intrinsic triangulations with edge lengths bounded by any fixed constant L naught. So we could take this constant L naught to be, let's say, the maximum edge length in the original, the length of the original path. Okay. And interestingly enough, this fact is also the crux of the proof that the Lawson intrinsic Delaunay flipping algorithm terminates with finite number of flips. Okay, so this seems to be a pretty fundamental theorem for intrinsic triangulations. In practice, just like this Delaunay flipping algorithm, it turns out we need very few flips. So this isn't like, you know, some exponentially many flips. It's really a practical algorithm. The same algorithm, by the way, works for closed loops, right? So I can start with some loop and find closed geodesics in the same isotopy class. One thing that's interesting about polyhedral surfaces is generically you don't have these closed loops, and so you can ask what happens on a convex domain. And what will happen is something actually quite nice, is it will contract to a discrete point. So a loop that just goes around a single degree 1 vertex, which is kind of cute. In geometry processing, there's also a lot of cases where we don't just need to consider a single path or a single loop, but actually we might have like a whole network of paths that are given by sequences of edges along the triangulation. And something we've said over and over again is, you know, there's really nothing special about the edges of the input triangulation. This is kind of just an artifact of the way we discretized or triangulated the surface. So for a lot of real applications, we might like to replace these initial edge paths with smoother, straighter curves, which we can do by running this FlipOut algorithm to convergence. Or maybe we don't want to run all the way to convergence. We just want to find paths that are straighter, but not necessarily straightest, or shorter, but not necessarily locally shortest. So we can just say, how about let's stop when the new length is within some fraction of the original length. So if I want to do like, if I have segmentation boundaries, I want to smooth them out. Okay, I can run this algorithm and get these nicer, straighter paths. We can also then start using this to build up other kinds of curves. Like if I want to construct Bézier curves on curved surfaces, on polyhedral surfaces, I can just run standard subdivision algorithms from the plane, right? And I'll get these beautiful geodesic Bézier curves. This is not our idea, but we can apply the same kind of thinking. So here's where it gets really interesting, when we start mixing geodesics with triangulation. So a really important idea in 2D is doing a constrained triangulation, where we ask for a maximal Delaunay triangulation that includes a given set of straight segments. Okay, and this is used for instance, this is how you might get a mesh for doing simulation, for describing your simulation domain. In the surface case, we now have a way of talking about straight segments and actually getting straight segments, right? So we can start with paths in the isotopy class we care about. We can run our flip-based geodesic algorithm. Okay, and now we have these geodesics, they're already sitting in a triangulation. So that's good news. We don't have to insert them in a triangulation. And all we have to do is improve this triangulation. So from here, we can do this Lawson flipping algorithm, or we can do Delaunay refinement, or we can do optimal Delaunay, or any of these other intrinsic algorithms to get a conforming mesh, a mesh that contains these geodesics. Okay. All these tools, doing this intrinsic constrained Delaunay triangulation, doing refinement, doing Bézier curves, makes it easy to construct some high quality meshes for all sorts of tasks in surface-based simulation and processing. So just like you would do in the plane, you want to solve PDEs, you have different boundary conditions that you want to prescribe on curves or edges. Now we can do all of the same stuff on polyhedral surfaces. Okay, it also, by the way, it's not really the problem that we want to solve is this classic problem of single source geodesics. So something a lot of people focus on is saying, I have a single vertex and I want to find the distance to this vertex. I want to find the minimal geodesic from this vertex to all of the vertices of the surface. I would say there's some very, very specialized and very fast algorithms for this purpose. So this is not really what I'm kind of advocating you use this algorithm for, but it is still pretty interesting to think about this and try this out. So kind of a simple way we could approach this is to start building a Dijkstra tree, right? So this would be a way of getting like an approximation of this single source geodesics. But rather than just using the ordinary Dijkstra tree, we're going to apply this straightening procedure kind of at the frontier of our Dijkstra search. So as we grow this tree out, we're going to straighten these curves so that they become geodesics rather than just edge paths. And what's really cool here is that at the end, we get a single intrinsic triangulation that contains in its edges all the geodesics to the source, right? So pretty crazy triangulation. Now, on the other hand, not all of these paths are globally shortest geodesics, but we do pretty well. So like in this case, about 95% of these paths actually are exact minimal geodesics. And for the ones that aren't minimal, they're no more than like a 1% overestimate, okay? And so it's really interesting to think about, like, well, why is this happening, right? Why do we do so well? We didn't put anything into our algorithm about being minimal. We just said locally we want to be shortest. Well, the intuition here is if you simultaneously have all of these geodesics crossing your surface, it would be really hard for them all to be too long, because if they were all way too long, then they would start crossing each other, right? And the fact that we have non-crossing geodesics, that we stay in the same isotopy class, keeps this from happening. We can't have these many overly long geodesics. But I think it's still a really interesting open question. Is there kind of a flipped-based strategy that guarantees that 100% of the curves are exactly minimal? Another nice thing we can do in the setting is we can also read off, once we have this kind of single source geodesic triangulation, we can read off at the source the direction of all the outgoing edges. And this gives us not only the geodesic distance or approximation of the geodesic distance, but also a very accurate polyhedral log map, which is useful for all sorts of surface processing. Okay, one last example is this headline that appeared in Quanta magazine not too long ago. And so the question that people were looking at, that they actually resolved, was to say, if you start at a vertex of a Platonic solid, can you walk straight, can you walk along a geodesic path and return to the vertex where you started without passing through any other vertex? And amazingly enough, this is something people didn't know for thousands of years. But the answer turns out to be no, except for the case of the dodecahedron. So on the dodecahedron, you do have this recurrent walk. And we thought, hey, just for fun, let's see, can we do this? And we can take a path on our dodecahedron and shorten it with the algorithm, and we get this same non-recurrent geodesic. So it seems like pretty powerful algorithmic tool for investigating the behavior of walks and paths on polyhedral surfaces. And so I would ask, all of you, are there any other interesting open questions you might be able to resolve about polyhedral surfaces using this kind of experimental algorithm approach? Okay, so what is the main takeaway of all this? Maybe the biggest headline is the title of the paper. You can find exact geodesic paths in triangle meshes by just greedily flipping edges. And what's kind of interesting about this is it's very similar to this greedy Delaunay flipping algorithm, but constructs very different kinds of triangulations, right? In this single source case, we construct a triangulation that looks nothing like the Delaunay triangulation. Instead, it looks like a triangulation that connects some vertex to every other vertex. And it's really nice for geometry processing that we can also use this algorithm to deal with loops and curve networks and so forth. And the most interesting thing, I think the most important thing, is that it's not just solving one isolated problem, right? We're really building up some machinery that lets us integrate lots of different tools from geometry processing, geodesics and triangulations and so forth, all in one framework, right? And that really helps to keep the algorithms simple and flexible. In the past, there's been tons and tons of work on polyhedral geodesic algorithms, especially for the shortest path problem. Like every year, I get asked to review more and more papers on faster and faster algorithms for solving the single source polyhedral geodesic problem. And I always kind of think, like, given how ridiculously fast the algorithms already are, this kind of race to the bottom on performance doesn't make a whole lot of sense, right? Already on triangle meshes with millions of triangles, we can find shortest paths in like milliseconds. And so kind of my 2 cents is that if you want to keep thinking about this problem, I think it's like a lot more helpful to the world to think about richer ways that you can integrate things like geodesics into broader geometry processing algorithms. Okay, so just to wrap up everything we talked about in the past 2 days, I just think about kind of what remains to be done. So we've come a very long way with this intrinsic viewpoint. I mean, in the smooth setting first, and then building up ideas about polyhedral surfaces and algorithms and so forth and data structures. But really, I think we've really just scratched the surface. And there's a bunch of interesting open questions in addition to the ones that we've identified throughout these 2 talks. So one question that David kind of asked about yesterday is, well, what about higher dimensions, right? I've been talking about two-manifold surfaces, can we do things for three-dimensional spaces? Well, the idea of intrinsic triangulation certainly easily extends to the n-dimensional case, right? I just have a topological triangulation with simplex-wise Euclidean geometry, nothing hard there. So one basic tool that we've used over and over again is this idea of an intrinsic Delaunay triangulation. What would an intrinsic Delaunay triangulation mean in higher dimensions? Well, actually, it's pretty straightforward. What you would do is just take pairs of n simplices that share an n-1 face, take those pairs and embed them in Euclidean space. If the circumscribing n balls are empty, then I would call that intrinsic Delaunay, okay? And that's an easy definition, but unfortunately, it's hard to actually construct such a thing. So even in the three-dimensional case, there's a theorem that you can't always reach a Delaunay configuration using what are called bistellar flips. So things that are kind of analogous to edge flips in the three-dimensional case. And kind of the basic reason, so how these look is depicted on the bottom right. So I can take these two tets that share a face and replace them now with three tets or vice versa. And you can show that actually you can't always reach a Delaunay configuration with these bistellar flips. The basic problem is, well, in the two-dimensional case, if I have a pair of triangles that makes a non-convex quadrilateral, then I know already it's Delaunay, right? I can show you very easily that will already be a Delaunay configuration. I don't need to flip it. In the three-dimensional case, you can have pairs of non-convex pairs of tets, which are not yet Delaunay, but are also not flippable, because if I try to do one of these bistellar flips, I'm going to get this self-overlap or this self-intersection. Okay, so this is kind of an open problem. Is there any algorithmic approach to constructing an intrinsic Delaunay triangulation in dimension greater than or equal to 3? Right? You don't have to use flips to construct this triangulation. You could try something else. So is there an algorithm for doing this? And in fact, do they always exist? Right? We don't even have, I don't think, an existence proof for intrinsic Delaunay triangulations in 3 dimensions. Another really important question is how to recover an extrinsic description from an intrinsic one, right? So we've been saying all along, oh, isn't it nice that we can just work with the intrinsic geometry? We don't have to think about how it's embedded in space. But there are a lot of times where you say, okay, I have this intrinsic metric. I would like to see what it looks like. Please at least, draw this for me on the screen. So the most basic version of this problem is to say, given a discrete metric, so I have, just lengths on edges of an abstract triangulation, I would like to find vertex coordinates in R3, let's say, such that the distance between those vertex coordinates realizes the given edge lengths. Okay, and in the convex case, you can do this. So Alexandrov very long ago proved that this was possible, and there's a nice algorithm by Bobenko and Izmestiev that actually uses this machinery of intrinsic edge flips to make this happen. Algorithms for the general, meaning the non-convex case, are still not completely satisfactory. So you can find some older kind of papers from geometry processing that kind of say, oh yeah, we can solve this problem. But actually, if you, on a careful inspection, you realize they kind of sneak in some extrinsic data like dihedral angles or normals or whatever. And then there are methods that use purely intrinsic data to embed an abstract metric. But generally, these have some things that are not completely satisfactory. So they might be kind of unstable, or they might give solutions that are like overly regularized. They're smoother than the actual metric was, or in general, they don't provide any hard guarantees that they actually will always work. And so the grand challenge here is to really, solve this for real. So I really want to be able to go out and measure, in the real world, geometry using lengths, not positions. I don't want a laser scanner. I just want to be able to take my ruler, take little measurements of length, and then recover the three-dimensional geometry. And by the way, I have this banana data set if you're interested in trying to solve this problem. Okay, so I said this is the most basic version of this problem. Why is that? Well, actually, it turns out this problem is harder than you might think. So the second version of this problem is to say, given an intrinsic polyhedral metric, find an isometric embedding in R3. Now, this sounds very much like what I just said. How is this any different from problem number 1? Well, the really important thing to realize is we don't know a priori which triangulation of the intrinsic metric can be embedded in a piecewise linear way, right? So for instance, there are lots and lots of different intrinsic triangulations of the cube. Not all of them can be embedded as a facewise linear embedding. Right? If I don't know how to bend these triangles, I don't know how to embed the surface. Okay, so the open question here is finding the embeddable triangulation actually just as hard as finding the embedding itself? Or is there something we can do that's kind of easier as a pre-process to first figure out which triangulation can be embedded before trying to solve the actual embedding problem? One kind of brute force thing you can do is you can always cut along all geodesics between all pairs of vertices. So this is something that we actually did try out, really slice up intrinsically all these order n squared vertices to embed, in this case, a cone metric. And then, by really pushing this hard, we can get some kind of embedding. But this is not a real algorithm that works, just a little numerical experiment. Okay, so just to summarize kind of all these open questions I've talked about so far in the last 2 days, a lot of questions seeking good answers. For one, intrinsic coarsening. We talked about inserting vertices in an intrinsic metric, and we remove them in some meaningful way. The efficiency of the intrinsic flip algorithm. So we've seen that empirically, this seems to behave pretty well, like almost like linear scaling. Can we explain this based on something about the geometry rather than just the number of edges of the mesh? There's a discussion of a vector Ripa theorem. So does the intrinsic Delaunay triangulation minimize some notion of smoothness for vector fields like it does for scalar functions? In the case of geodesics, can we modify this flip-based algorithm to make sure that we actually have 100% minimal geodesics rather than just almost all minimal geodesics? In terms of triangulation, can we extend this idea of intrinsic Delaunay triangulation to dimensions 3 or greater? Is there an algorithm that will actually construct these things? In terms of discrete Laplacians, is there kind of a more geometric notion of discrete locality than the one we usually consider? And can we recover the geometry, the extrinsic geometry from our intrinsic metric? I mean, that's a classic and long-standing problem. Certainly not a new open question that I'm proposing, but definitely one that's really relevant in this context where you're doing geometry processing from the intrinsic point of view. Okay, and there's lots and lots more. I mean, I could go on with more open questions. So if you think you have an answer or you want more questions to think about, let's talk. I love this stuff, so I'm glad to chat with you more. Before wrapping up, I also want to mention that there is free and open source code for many of the data structures and algorithms that I've shown. So please go ahead and try them out if you'd like. We'd love to hear about what does and doesn't work for you. So especially my student Nick is doing a lot of great work on developing this code and making it usable and useful. And so just to summarize kind of the last 2 days, I think like at a very, very high level, this topic of intrinsic triangulations is a terrific example of how kind of math and computer science can work together to create some beautiful and useful stuff, taking some deep theory on the mathematical side, Riemannian geometry and normal surfaces and hyperbolic geometry, and connecting that to some really important contemporary problems like doing robust geometry processing. What we have kind of already provides a lot of utility for geometry processing. So we saw a lot of different quality guarantees for surface meshing, structural guarantees for differential operators, convergence guarantees for mapping, bridging between manifold mesh processing, point clouds, and so forth. And kind of getting a sense that this is another sort of Swiss Army knife for geometry processing. But there's definitely a lot of open questions remaining. There's definitely a lot of practical work that still needs to be done to make this stuff really useful. And I hope that I've inspired you to think about at least some of these questions. And as I said, always glad to chat more. Okay, thanks a lot for your attention.
Okay, thanks, Professor Crane, very much for this very wonderful talk and inspiring questions. Okay, I believe people must have a few questions for Crane. Yeah, let's see.
I do actually. I think I'm the first one.
Okay,
cool.
Go ahead, please.
Yeah. So far with the intrinsic meshing, I think I see that we only apply it to the mesh that don't deform, right? But like when we do like soft body simulation, sometimes the mesh geometry does deform. So is this applicable at all?
Yeah, so we saw one example earlier where you're talking about a mesh that changes over time, this minimal surfaces, right, where we're constructing these soap bubbles. So each step, I didn't show kind of the progress of this algorithm, but each step this mesh is changing. And so basically it's kind of, I think I kind of said this yesterday, if you have a problem where you can think of your extrinsic geometry as a signal that's evolving over the intrinsic domain, then you can solve this kind of problem. It is definitely difficult if you change the extrinsic geometry to update the intrinsic triangulation. That is certainly difficult. We've had some thoughts about how you can do that, basically because your geodesics totally change, right? If I start dragging on vertices in space, the geodesics change. And so maybe the best thing to do is just start over from scratch and rebuild your intrinsic triangulation.
I see.
So we've thought about how to do that incrementally, but you're right. Like that's something where, more thought is required.
Cool. Thank you.
I see the second person is Erin. Yeah, go ahead, please.
Thanks. So I'm probably going to reveal that I'm a theoretician here and not all about practicality. Particularly for the geodesic algorithm, suffers from the same thing where it's sort of that it terminates, but it works really fast. Is there an underlying proof there? Is that just going to be as hard to prove as all of these other termination bounds for why they're working so practically well?
I see. Yeah, you're saying is there any proof of efficiency rather than just proof of termination?
Exactly.
Yeah, no, not at all. And I think, I don't know. I mean, which one would I attack first? In terms of trying to figure out, why is it efficient? I think I would start with Delaunay flipping and think about why that's efficient. Because it's just kind of a simpler problem, a simpler algorithm. And I think that probably if you could get your head around why is it that Lawson's algorithm works so well, in the case where you start with an embedded metric, or a metric where your metric comes from an embedding, then that might give you some ideas about why it works in the geodesic case as well. But yeah, I don't have any. I've had like one student kind of look at this, but don't really have any strong leads. I've actually talked to Jeff also a little bit about this. So I think that's like definitely a problem worth hacking on. It's a really cool problem.
Thanks.
Okay, Joe, it's your turn.
Hi, Keenan. When you do the flipping to compute these geodesics, is this done using the intrinsic ideas from yesterday, or do you do it extrinsically for surfacing R3?
Yeah, it's always intrinsic. It's intrinsic, so you do these intrinsic flips, but then the final path you have is a geodesic along the extrinsic polyhedral surface. So if you want this as a path in three-dimensional space, you can just read off the places where the intrinsic path passes through the extrinsic edges.
Right. So in the end, it's not stored as, if you think in terms of the original triangulation, you don't store it as edges. So it's not going to be edges of that triangulation. You can't triangulate extrinsically to get it to be a geodesic, I guess, right?
Yeah, well, you could just take the common refinement of the extrinsic and intrinsic mesh, and now you'll have an extrinsic mesh that contains your geodesic as edges.
Okay, very good.
Okay, Owen. Yeah, go ahead, please.
Yeah, okay, thank you. Hello, very nice talk. I was wondering on the problem where you have a single vertex as the source for all geodesics, where does the 1.5% for the error come from? Like, is that proven?
No, sorry, that was only for that one example that I showed on the slide.
Oh,
I was just reading off some statistics for that example, and that's generally our experience with other examples, but it's experimental, right? You could probably find some pathological case where it's worse, or but just to give a general sense that because these geodesics can't cross each other, it's pretty hard for them to be much longer than the minimal geodesics.
Okay, so is there like progress into a theoretical understanding of this, or is it so far only experimental?
Not really. Nick, I think, has thought about it a little bit and hasn't gotten anywhere with it. So that's why I put it as an open question on my slides. So if you want to think
very
about
interesting.
it.
Yeah. Thank you.
Okay, Nina, go ahead.
So, do the geodesics that you get, do they pass through a lot of vertices of negative curvature?
They can.
In practice?
It just depends. Yeah, not a ton. So usually, like kind of models you encounter in real life, you might pass through a few saddle vertices. So you have, I don't know. I actually don't know off the top of my head, whether it's like a dozen edges or something, but yeah, it's not a ton of saddle vertices.
Okay.
In kind of the extreme case. A lot of the time it's just one edge. It's just one edge that doesn't go through any saddle vertices as well.
Okay, yeah.
It just depends on how your model looks, Higher genus, you probably have more saddle vertices and so forth.
Yeah.
Okay, let's Jack to ask the last question due to time limit. Thanks for understanding. Hi, Jack, go ahead.
I'll keep it very short.
Okay.
Related to Joel's question and to the question I asked during things. So it seemed, if I'm understanding this correctly, if you ran this on your tufted, you could do it if you ran it on a tufted representation. If you started with something orientable, you'd get back both the geodesics as edges plus the originals, right? Is sort of the opposite side. And you get back both of the meshes and just have to then sort of stitch them back together again, right? Am I understanding that correctly?
Yeah, that is a really good question. I mean, it's kind of, I feel embarrassed. I haven't thought, given those were the two topics I presented in this talk, I haven't really thought that much about what happens when you run the geodesic algorithm on the tufted cover. Does that give you actually the shortest path on this non-manifold domain? I don't know. I definitely don't want to say yes because I just don't know, but that's an excellent question.
Well, the follow-up was going to be, what if you run it on a non-orientable surface as well? So then you can think about that one too.
If it's non-orientable, I mean, all of this machinery, by the way, should work out fine, even without this tufted cover. It should all work out fine on a non-orientable domain.
Oh yeah, sure. I mean, the tufted cover becomes interesting on a non-orientable surface because you'd wind up going twice around your Mobius strip or something like that instead of just a straight geodesic. But okay.
Yeah, that's a fun experiment though. Yeah, I'll definitely think about that.